Today's lecture is going to be more about non-deterministic finite parameter. For the first part, we'll make sure that we understand non-deterministic finite parameter very well. And in the second part of the lecture, we will talk about converting an NFA into a DFA. So let's take this example to start the discussion. L W such that W contains 1, 0 as a substring. Contains the substring 1, 0. Now, this is very straightforward for containing a substring. The NFA for this is straightforward. So you just you have to have the 1, 0 somewhere. And then you just say, before the 1, 0, I can have anything. And after the 1, 0, I can have anything. And that's all what you need. Now let's trace some strings. Now we're not going to do the tedious tracing that we did last time. So that detailed tracing that we did last time is something that we're not going to do again. We just did it so that you fully understand how an NFA works. But now, that tracing, you can do it in your head. You're not now, after seeing that detailed tracing that we did last time, it should be easy to do that tracing in your head. You don't have to draw all of those branches. Okay. So now what about this string? So how will it work in the NFA? So in the NFA, we get a 1. The 1 keeps us in Q0. Now we get this 1. Now first of all, the first one kept us in Q0, but we had two options. Right? We had two options, either going to Q1 or staying in Q0. So how did we make the option of staying in Q0? Yeah, okay, go ahead. How? Why did we decide to stay in Q0 with this one?
Since it doesn't have 1, 0 as a substring.
Oh, yes.
Maybe because we're going through our options, so we just chose to go through that path first.
Well, going through all options, that's an important point. That's a good point. In your head, this is simple enough. This NFA is simple enough for you to go through multiple options or multiple paths in your head. So in your head, you are doing the tracing that we did last time, and you are exploring multiple options, and you figured that if I use this option and go to Q1, I'm not going to get to I forgot the accept state. I'm not going to get to an accept state. If I use this option here, if this one takes me here, then what? Then the second one will take me where? To nowhere. So it's going to be a dead end. So if I take this option is going to dead end. It's like here, you are in Q0, and you have, on a 1, you have two options, either going to staying in Q0 or going to Q1. Now with the second one, if I am in Q0, when I get the second one, I have the options of staying in Q0 or going to Q1. With Q1, if I get a 1 when I'm in Q1, this is going to dead end. So you did this in your head and you said, okay, I'm trying to get to an accept state, and to get to an accept state, this is the path in red here. This is the path that's going to lead to an accept state. So there are multiple paths. Some of them may dead end, some of them may get you to an accept state, and in order for a string to pass, you have to have at least one path. One path that ends in an accept state. That's all what you need. You don't need more than one path. So that's why you chose with the first one to stay in Q0. With the second one, you chose to proceed to Q1. With the zero puts you here in Q2, which is an accept state. So the 0 is going to put you in Q2. Now 0 from Q0 is going to, you'll stay in Q0, but this is not the path that will lead you to acceptance. So this is the good path that will lead to a Q. And Q2 is an accept state. And then when you get the last one will stay in Q2, which is an accept state. So if the NFA is simple enough, then you will do all of these paths in your head and you'll pick the path that will lead to acceptance, and this will get accepted. But if I give you a string with that doesn't have 1, 0 as a substring in it, like 1, 1, 1, there is no way for this path to get to an accept state. Even if you look at all options, with this one, whether you stay here or you take this, eventually you're not going to get to Q0 to Q2, which is an accept state, unless you have a 1 followed by a 0 somewhere. And this doesn't have it. So there is no way for this to, there is no path that leads from start state to an accept state with this string. So this is going to be a reject. Now what about this? What about this string? So when we are in Q0, what should we do? Should we choose to stay in Q0 or go to Q1 with this one? Which option should we take?
Go to Q1.
Go to Q1. Well, the answer is...
You can do either.
Who said either? Yeah, that's the right answer. Either option is going to lead to an accept state. Whether you go to Q1 or stay in Q0. That's why it's a non-deterministic finite automaton. So let's choose to stay in Q0. If we stay in Q0, right, so the first one will keep us in Q0. The 0 will keep us in Q0 again. The third one will take us to Q1. The 0 will take us to Q2, which is accept. So this is one path. The other path is you can go from Q0 to Q1 with the first one. So you can choose to go to Q1 with the first one. Then with the 0, you go to Q2. Then you loop on 1 and 0 in the last state. So basically, you have two options. With 1, 0, 1, 0, you can either think of this as the match and this as anything.
Or vice versa.
Okay? Or you can think of it the other way around, which is this is the anything and this is the match. Okay? Two different ways, two different paths, and that's why the non-deterministic finite automaton is non-deterministic. Non-deterministic doesn't mean random, it means you have multiple options. Any questions on non-deterministic finite automaton? Anyway, so you'll get to practice this in the first homework assignment that I have posted last night. Now, so now the next topic is converting non-deterministic finite automata to deterministic finite automata. So NFA to DFA conversion. Now the idea, by the way, let me ask a question first. Now this is for an NFA, how an NFA can be traced. Now what do you think if we were to draw the same graph for a DFA, what will it look like for a DFA? Yes. Yes.
It would just go down one straight path.
There will always be a single, one unique path. So for a DFA, there will always be, it's just going to be like this, always one path. It will be just a one-line graph. It's deterministic. You don't have branches, you don't have multiple options. You always have a single option, one unique option, that's it. Now, this is the DFA. So the NFA has branches, the DFA doesn't have any branches. Okay. But in fact, whether you are talking about an NFA or a DFA, what would be the depth of this tree? In both cases, whether it's an NFA or a DFA, what will the depth of the tree be? So this is a tree that has only one branch at each point. And this is the tree that has multiple branches. But in both cases, what's the depth of the tree?
4.
It depends on what in general. Generally speaking, what's this?
How many symbols you have?
How many symbols where? How many symbols in what?
String.
In the string that we are processing. Yes. So the depth of the tree is dependent, or is in fact is equal to the number of symbols in the string that you are processing, whether it's an NFA or a DFA. So this is one observation. Now, in order to make the NFA become a DFA, become deterministic, the key idea is to think of this set of states that we can reach in an NFA, think of it as a state, as a single state. So define a state that you call Q12 or Q01 here. Think of this as one state. So you're saying that when you get a 1, you go from Q0 to a state called Q01. And this Q01 is a state in the DFA, in the equivalent DFA that we're trying to construct now. We're trying to convert an NFA to an equivalent DFA. So in our equivalent, so let's use a different names like D. So this is D0. D0 consists of Q0 by itself, and D12 consists of Q0 and Q1. And this is D12 again. This is another combination of states. You can think of it as another combination. So this is the state D02. So thinking of a combination of states in the NFA as a single state in the DFA that you are constructing will allow you to convert any NFA into a DFA. Okay. This is the idea. Now, this will make more sense when we look into an example. So let's take a concrete example. By the way, this procedure for converting NFAs to DFAs is called the subset construction. Why is it called the subset construction? Why do you think it's called the subset construction?
Is it because there's, as far as in the NFA, one path is just a sum of the myriad of different paths that can be taken?
No, it's not the path that is a subset. What is a subset of what? Something is a subset of something else. So it's not a path. It's not about paths. It's about states. So the state in the DFA that we are constructing is a subset of the states of the NFA, the original NFA. Okay, so far it's abstract. Now when we go through a concrete example, things will make a lot more sense. So let's take this concrete example. Okay, so the Q2 and a transition on B, and I have a transition on B and a transition on A or epsilon. Okay, so clearly this is an NFA, not a DFA, because I have an epsilon transition. And because what? What else makes it an NFA?
It doesn't say what to do with Q2 get to A.
Yeah, exactly. There is no transition, there is no A transition out of A2. So this is an NFA. Now, we will be converting this NFA into a DFA. Now, knowing that in the target DFA that we are trying to construct, a state in the target DFA is going to be a subset of the states in this NFA. So how many subsets are there of this set of states? We have Q1 and Q2. How many subsets? What's the total number of subsets? 3 subsets? No. There are more than 3 subsets. So what are the 3 subsets? There are 4 subsets. So tell me the 3 that you know.
I don't know.
So the subsets are, the first subset is Q1 by itself, is a subset. The second subset is Q2. The third subset is
Q1, Q2,
Q1, Q2.
and then Q2, Q1.
And what's the fourth subset?
Q2, Q1.
Nothing. The third subset is the empty set. 5. So you have exactly 4 subsets of this set of states. So this is the power set. The power set of this set has all possible subsets. So you can either have Q1 by itself, or Q2 by itself, or Q1 and Q2, or nothing. Now what if we have 3 states? When we have Q1, Q2, Q3. How many subsets do we have?
9.
No, not 9.
10.
6.
What's the mathematical relation between the number of elements in a set and the size of the power set of that set?
To the n.
2 power?
At the end.
Yeah, 2 power n. So if you have a set of n, if you have a set of size n, then you have 2 power n subsets. That's the power set. So for this, we have 3. N equals 3. You have 3 states, then you will have 8 subsets. And these 8 subsets are Q1 by itself, Q2 by itself, Q3 by itself, Q1, Q2, Q1, Q3, and Q2, Q3. What else?
No.
All of them is another subset. Q1, Q2, Q3. And what's the 8th subset? The empty set. Yeah. So this is what we are trying to reach, because a state in the DFA that we are trying to construct is going to be a subset, and we have to make sure that we cover all possible subsets of the set of states in the NFA that we are trying to convert. Okay, so the number of subsets is going to be 2 power n. We'll talk more about this exponential function later, because in algorithms, exponential is always a problem. Okay, so now I'm going to do this. I'm going to do, this is I'm going to call it Q1. To avoid using the same name, I'm going to use D instead of Q. So I'm going to call this D1, and then I'm going to have a D2, and then I'm going to have a D12, and a D what? D5. These are the subsets. Okay, I think we need this part of the board to calculate the different transitions. Okay, so how does this work? So we have constructed all the, so this is an NFA. This is a DFA that we are, an equivalent DFA that we are trying to construct. Now, we need to figure out the transitions in this DFA in order to get the same and equivalent behavior to this. Now, when we are in Q1 and we get an A, where should we go? To Q2. So, Q1 with an A, you go to Q2. Simple. Now, if you are in Q1 and you get a B, where do you go?
Stay there.
So, yeah.
No, not stay there. You have another option. If you are in Q1 and you get a B,
You can also.
You can go to the null.
you can either stay in Q1, right? Or you can go to Q1 but use the epsilon transition to go to Q2. You have two options. And this is the key idea. If you miss this, you miss the whole point. You have to take into account all possible options. If you miss an option, then your DFA is not going to be correct. In order for your DFA to be correct, you have to capture all options. And this option, if I have a Q1 and a B, I can go to either Q1 or Q2 because of the epsilon transition. Okay? So you have to follow the epsilon transitions. If you don't follow the epsilon transitions, your conversion is going to be wrong. So that's why if I am in Q1 and I get a B, I go where?
D12.
D12. This is the key idea. Okay. Now, in general, like if you have, we have the notion of the epsilon closure of a state. So if you are in Q0 and then you have Q1, okay. So we have the notion of the epsilon closure of a state. But let's say the epsilon closure of Q0. Okay, so let's add this. Okay. Now, the epsilon closure of Q0 is Q0 itself plus all the states that can be reached from Q0 via epsilon transitions. So the epsilon closure of Q0 has Q0 itself. It will always have the state itself. And it will have Q1. It will have Q2 in it. Will it have Q4?
No.
No. Q4 cannot be reached
Right.
via epsilon transitions, but it will have
Q5.
Q5 in it. So the epsilon closure of Q0 is the set of states Q0, Q1, Q2, and Q5. So in doing this NFA to DFA conversion, whenever you get you go to a state, you want to make sure that whenever a transition takes you to a state, you want to make sure that you include the epsilon closure. So for example, in this case, what about delta of Q0 and Q1? Sorry, delta of Q0 and A. If I get an A, when I'm in Q0, then I will go to Q1, but then the epsilon closure can take me to Q2 and Q5. So when you do the conversion, if the A takes you to a state, you always have the option of taking epsilon closures to other states, and you should cover all possible epsilon transitions, and not only the one-step transitions, but all of them. Yeah. Okay. So now what I have done so far is, from D1, I have done the transitions for A and B. Then I need to do the same thing for D2. If I'm in Q2 and I get an A, do what?
Nothing.
Nothing. You go to the null state, or to the empty set of states. So this is like going to a trap state. So in fact, in the DFA, in the final DFA that we will be constructing, this D5 will serve as a trap state. Because obviously, there are no transitions out of this D5. Why? Because the empty state does not appear in the original NFA. So there are no transitions out of it. Every transition will keep you in D5. By the way, our sigma is AB clearly. Okay, so now if we are in D2 and we get an A, we go to D5. If we are in D2 and get a B, yeah, you go to Q1, but then you have the option of taking an epsilon transition to Q2. So whenever you go to Q1, you will never stay in Q1. You always have the option of going to Q2. That's why Q1 is going to disappear at the end. You'll never stay in Q1. So that's why you don't care about transitions out of this Q1. So you'll never stay in it anyway. So if you are in Q2 and you get a B, you go to Q1, 2. Okay? Is everyone following this? Okay, what remains? What should we do next? Is this complete? Yeah. It's not complete yet. There are lots of things that we need to do. It's what's missing?
We don't have a final state.
Yeah, what's coming out of D1? The transitions of those new states that we have introduced. In fact, D1 and D2 are straightforward, relatively straightforward, because they existed in the original NFA. But now this thing did not even exist in the original NFA. But in the original NFA, this is a combination of sets, a combination of states. So in fact, what makes sense for the transitions of delta of D12 and a symbol X is going to be equal to delta of D1 on symbol X union delta of D2 on symbol X. So basically, in order to figure out the transitions for D12, look at the transitions for D1, transitions for D2, and take the union. Does the union make sense here? Why does the union make sense? So we need the rationale. You know, why are we doing the union? Because in the NFA, we're taking all options into account. So you have multiple options. So being in D12, what does being in D12 mean? It means that you are either in D1 or you are either in Q1 or in Q2. So you are either in this or in this. So being in this or in this means that you have multiple options. So you have to take into account the options, the transitions out of this and the transitions out of this. So it's like you are in Q12. So D12 is just this, Q1 and Q2. So you are in this state. And the transitions out of this are this. All the transitions out of Q1 and all the transitions out of Q2, and you union them. You add them together. Okay, so now here, let's be specific. Delta of D12 and A is what? Sorry, D1, 2 and A, yeah, it equals delta of D1 and A union delta of D2 and A. And delta of D1 and A is D2 union delta of D2 and A. Where does this go? Phi. So it's going to be phi. So it's like D2 is in fact the set Q2 union the set phi, and that's going to give you the set Q2. So the transition on 1, 2 is the transition on 1 for an A, which takes you here, and the transition on 2, which takes you to the null state, which means that the union is going to be what? D2. So the A is going to take you to any questions on this? Is everyone seeing why it takes us to D2? Okay, now what about delta of D1, 2, and B? So this is going to be delta of D1 and B union delta of D2 and B. And D1 and B takes you to D12. In fact, I stopped there because this already has all possible states. So Q12, this already takes you to the state that has all the states in it. So unioning this with anything else is going to give Q12. So there isn't anything to add. Okay. So, but this is D2 and D. D2 and B is, again, is going to go to the same state, so the state union itself. So D12 and B is going to keep you in D12. Okay, so now we have a transition for A, transition for B out of each state, and we have exactly one transition per symbol. We don't have any epsilons here. This is a DFA. Well, it's not quite. What remains? What should we do in order to make it a DFA? It's not yet. So all the transitions are there, but what do we need? Yes?
An end state? Accept state?
An accept state and a start state.
Yeah.
So you need a start state and an accept state. You need both. Otherwise, well, in fact, the start state is necessary. You must have a start state, but in theory, you don't need an accept state. If an NFA or a DFA doesn't have an accept state, then it's a valid NFA or DFA. But in this case, what will be the language that this NFA or DFA accepts?
All. Everything.
No, if it doesn't have an accept state at all. So if I draw 1,000 states like this without an accept state, So I keep throwing states with no accept state, and there's a million of them. What would be the language accepted by this? It's the language part. So this is the language. Don't underestimate this. This is a language. The language that has no strings in it. Okay, so this is a language. It's not probably useful. Well, in fact, it's useful. It's having the phi, the empty language, is useful. Because here it acts like in this conversion, it acts like a trap state. But anyway, so you need a start state, and you need to identify the accept states. So what's the start state? No, in fact, the start state is going to be the epsilon closure of the start state in the original NFA. So let me write this down. The start state in the target DFA is the epsilon closure of the start state in the original NFA. And in this case, it's going to be the epsilon closure of Q1. And what's the epsilon closure of Q1? Yeah, D12, Q1, Q2, which is D12. So this is indeed our start state. Now, what does this mean? It means that Q1, when you are in Q1, you are not actually in Q1. You are in Q1 or Q2 because you can always transition from Q1 to Q2 without processing any symbol in the input string. So if you are in Q1, you are actually in the union of Q1 and Q2. And that's why the actual start state is D12. So this is our start state. Now, what should our accept states? Logically, what should the accept states in the DFA be?
D1. D1.
D1, no, not true. Not only D1. D1, yes, belongs to the set of accept states.
But you wouldn't be able to get to it.
That's why we'll take care of this later. Okay. Okay, we'll take care of this later. But at this point, D1 belongs to the set of accept states. And what else belongs to the set of accept states?
D1,
D2? Why would D2 belong to the set of accept states? Okay, when we do that transition, that tracing of the NFA, how did we determine if a given state is an accept, like if we have Q1, Q2, Q3? What would determine if this set of states is an accept state or not? If it has at least one accept state in it, in the original NFA, right? So being in D12 here means that we are either in D1 or either in Q1 or in Q2. So this is an OR of Q1 and Q2. So being in this means this is equivalent to being in Q1 or Q2. It's like this. You are in Q1 or Q2, and Q1 is an accept state. So this is an accept state. So who can generalize this? How do we pick the accept state in the DFA? Who can generalize this? Make a general statement. Generally speaking, the accept states in the DFA are what?
The same.
They're not the same. Here I have only one accept state. Here I have two accept states. So how would we generalize this? Any state that corresponds to a set of states that has in it an accept state in the original NFA. So each state in the DFA is a subset of states, or is a set of states. Each one is a set of states. And if in this set, at least one of the elements of this set of states is a state that was an accept state in the original NFA, then that's an accept state. So to make it simpler, the accept state here is 1. Anything that has a 1 in it is an accept state. Does this sound simpler? Yeah, because that's the concrete. For this concrete example, U1 is the accept state. So anything with a 1 in it is going to be an accept state. Because this is 1 by itself, and this is 1 or 2. This is what this means. So keep in mind, what does this mean? It means that I'm either in Q1 or in Q2. So now I have a perfectly complete DFA with all the transitions, with a start state, and with accept states. Yes?
Could you write down the abstract of it?
The abstract of what? For the accept state? Yes. Okay. Okay. So a state in the DFA is an accept state if at least one of the states that constitute this state corresponds to an accept state in the original NFA. So the states that constitute this state, so that what does a state that constitute, the states that constitute it, or that this state consists of, corresponds to an accept state in the original NFA. Because this DFA state is a composite state. So this is a composite state, or it's a set of states. It's actually a set of states. A state in the DFA is a set of NFA states. So one of those states in that set should be an accept state. Okay. Okay. So now what's missing? So this is the DFA, but we can simplify it. This can be further simplified. Why?
Well, none of the paths go to D1, so could you just take it out?
Yeah, exactly. So D1 is an unreachable state. Of course, if I keep it like this, it's correct, but it's not minimal. So it has this state is unreachable. And an unreachable state can be eliminated. You don't need it. So you can keep it, but you don't have to keep it. So in order to simplify things, or to use the minimal, to consider the minimal DFA, we just do this. D12, which is an accept state. And then if I get a B, I stay in D12. And if I get an A, I go to D2. And if I get an A when I'm in D2, I go to a trap state. I go to a trap state. What else? If I get a B when I'm in D2,
You're back.
I go back to D1, 2. So whenever you do this, you need to check if you have, all the transitions in there. So I have, for D1, 2, I have a transition for a B, transition for an A, I have a transition for an AB, AB. So you have all, in this case, all 6 transitions. 3 states, you have to have 6 transitions exactly. Okay, so is this equivalent to this? Yes.
Is D1 unreachable because there's no path that leads to D1?
Yes. There is no path that leads to D1. By the way, how can you detect this algorithmically? Thinking of this as a graph, how do you detect unreachable nodes in a graph? How do you detect unreachable nodes in a graph? So you just do a traversal. So this is, so you do a traversal like DFS or BFS. Traversal starting from where? Start. So if you do a traversal from the start state, all the states that you can reach are reachable. And the states that you can't reach are unreachable. Okay, that's what, yeah. So traversals can solve the reachability problem for you. So this is the, what we call the subset construction for converting an NFA into a DFA. Look at this DFA and try to convince yourself that this is equivalent to this. Well, you can do this by checking some sample strings, right? Any string that is accepted by this should be accepted by this. And any string that is rejected by this should be rejected by this. And if you can find at least one string that is accepted by one and rejected by the other, what would this mean? That there is something wrong in our conversion. They are not equivalent. So if there is at least one string that is rejected by one and accepted by the other, then the conversion is not correct. So you should check for an error in your conversion, if there is such a thing. So it's good to do some checking and to make sure. So what does this mean, this NFA? So if you get a B, you are there. If you get an A, you go to this. So basically, what this is saying is that if you get 2 consecutive A's, you will get rejected, right? Because if you get an A, the A takes you here, and once you are in this state, nothing will take you to an accept state except a B. You need a B to take you to an accept state. So if you have 2 consecutive A's, you will get stuck here. The first A will take you to this, and then the second A will take you to a trap state, an implicit trap state in the NFA, which we made explicit in the DFA. So trap states are explicit in the DFA, and implicit or can be implicit in the NFA. So there is an implicit trap state here that we made explicit. So one of the things that we do in this subset construction is making trap states explicit. Okay, any questions on this conversion? Does it make sense? Yes.
So pretty much, can all NFAs be made into DFA?
Well, this is an excellent question. Who can answer this question? Yes?
Every NFA can be made into a DFA, but not every DFA can be made into an NFA?
No. In fact, every DFA is already an NFA. A DFA is already an NFA, like a doctor and a surgeon. So it's DFA. Every surgeon is a doctor, but not every doctor is a surgeon. Okay? Okay, so is this, the question that was asked is, can we convert any NFA? So do you think that this procedure is general enough? Can you think of any kind of NFAs that cannot be converted into NFAs, into DFAs using this procedure?
Yes.
Yes.
If there's enough, like it's saying W has to contain several things, like a 1 0 and a 1 1 and another. So wouldn't that be too complicated?
Okay, forget about the language itself. Think of the NFA. What we described is a general procedure. It can be applied to any NFA, and you can convert any NFA to a DFA using this procedure because the procedure is general. You just look at these, you take all possible subsets, and you do the transitions, so it's very general, very systematic. You do the transitions for the original states, and you take into account the epsilons. Then you look at the composite states. By a composite state, I mean a state that corresponds to multiple states in the original NFA. And then the transitions for composite states are the unions. So this is a very general procedure. And if you think that it's not general, you need to give me an NFA that cannot be converted into a DFA using this procedure. And then I will convert it for you, and I will convince you that this procedure is general enough to convert any NFA into a DFA.